So let me start my presentation, my talk. Sorry. So I would like to present a talk on the Lyapunov approach for the analysis of time delay systems. But let me start with the delay-free case just to recall some main concepts, main results based on the Lyapunov approach. So here is a linear time invariant system. It's delay-free. Matrix A is a constant matrix. Here are some main notions for such systems. The state of the system. The state of the system is x of t. So this is the state at point t. And this is just a vector. Usually it's a real vector, but maybe it's a complex one of the dimension n. N is the order of the system. X of t x0 is called the solution of system df, corresponding to the initial state x0 and the initial time instant t0. Without any loss of generality, we can assume that t0 is 0 as we deal with time invariant systems. And here is a general formula for the solution. No, it's simple for delay-free systems, just the fundamental matrix multiplied by the initial state. The fundamental matrix is the exponential matrix of matrix A of the system. System df is exponentially stable, is called exponentially stable if there exists positive constant gamma and sigma such that for any initial state, we can estimate the solution, the corresponding solution by such inequality. So there are different approaches for the stability analysis of such systems, but we concentrate on Lyapunov approach. The Lyapunov matrix V is the matrix which satisfies such equation. This is the classical Lyapunov matrix equation. W is an arbitrary positive definite matrix. So this is a well-known Lyapunov criterion. A system is exponentially stable if and only if the Lyapunov matrix is positive definite, the Lyapunov matrix V. It's worth mentioning that the Lyapunov matrix can be explicitly expressed in the case of exponential stability of the system. It can be expressed as an improper integral of the fundamental matrix K, which is exponential matrix in fact, and this matrix W. This formula is working only if the system is exponentially stable, because otherwise the integral deserts. But this formula, which is the Lyapunov equation, holds for both exponentially stable systems and unstable systems, except maybe some critical cases where we have eigenvalues which are opposite with respect to the imaginary axis. Thus, this equation is much more general than this explicit form. Okay, the Lyapunov approach also allows to solve some other problems, not only the exponential stability analysis, but also first application is well known. It's the construction of exponential estimates for the solutions. If we construct the Lyapunov function V based on the Lyapunov matrix V capital, then we can differentiate this quadratic form along the solutions of the system df, and we obtain another quadratic form which is negative definite. So this quadratic form is positive definite, but with minus it's negative definite. Obviously, we can write this inequality, where sigma is a number which can be estimated by such a fraction. From this inequality, we immediately obtain such a conclusion that the function exponential multiplied by v is non-increasing along the solutions of the system df. And from this fact, we derive the desired estimate. So this is the same estimate like in the definition of the exponential stability, with sigma defined by this formula and gamma is the square root of this fraction. So the estimate can be easily computed. Another application of the Lyapunov method is the robust stability analysis, if we consider the nominal system, and another one which is the perturbed system. F is considered as a perturbation. F is not necessarily linear, maybe it's non-linear, and even time varying. But we assume that this is bounded by such a product, by a linear function. Again, if we differentiate the function v along the solutions of this new system, then we obtain two summands. First summand is the same like in the previous case, and the second summand depends on the perturbation. It's can be easily estimated from above, and to guarantee that the zero solution of the perturbed system is exponentially stable, we need to assume that this derivative is a negative definite. So we obtain this theorem. The solution is exponentially stable of the perturbed system if the nominal system is exponentially stable, and this parameter alpha is less than the fraction. There are also some other applications of the Lyapunov method. You can compute the H2 norm of the transfer matrix of the system. You can compute the quadratic performance indices in optimal control tasks. You can design the control law, a stabilizing control law, and so on. Also, optimal control law by step-by-step procedure, by iterative procedure. You can look works of Zubov to know more about this approach. Okay, but I would like to talk about time delay systems and to show how this concept can, how the Lyapunov approach can be generalized for this kind of systems, and how to solve the similar tasks for these systems. So first, here the simplest possible retarded type system, just two terms on the right hand side, delay-free term and the delay term. All the parameters, matrices, and h are constant, and h is assumed to be positive. A more general case is a system with multiple delays. Also, sometimes the systems with distributed term are considered. So such kind of delay is called pointwise delay, and this sort of delay is called distributed delay. G is maybe continuous or piecewise continuous, or even L2 function, matrix function. Also, there are more complicated types of systems, neutral type system, for example. Here, the delay is not only on the right-hand side, but also under the derivative. Here, matrix D is a matrix such that this operator, the operator under the derivative, so the difference operator, in fact, is strongly stable. That was the systems of that was time invariant systems, and also there are some time varying cases. Here the delay is time varying. Sometimes the matrices are time varying, and for instance, the case of periodic matrices A0, A1 is very important in this theory. Also, it can be a system with a distributed term. So, but but in this presentation, I would like to consider on the simplest case, the linear time invariant system with a single delay. two main concepts for this system. The first one is the state of the system. I recall that the state of the system for delay-free case was a vector. So just a vector x of t is a state for delay-free system. But for time delay systems, the state is not a vector anymore. It's a function. So xt is a function which is defined on the segment minus h0 and is at least piecewise continuous. Sometimes it's considered to be continuous. It depends on the approach that you apply. We can conclude with this that the system, the time delay system, is infinite dimensional in contrast to delay-free case. X of t phi is a solution of system corresponding to the initial function, initial state, initial function phi at the time instant t0. Here is a definition of the exponential stability. This is exactly the same like for delay-free case, but with a different norm on the right-hand side. Before we had initial state to be a vector, and we used vector norm. Here we have the function as an initial state, and we're using functional norm. This subnorm from C0 Banach space. Okay, next definition is the fundamental matrix. As I told above, the fundamental matrix for delay-free system is just an exponential matrix. For time delay systems, this is not so simple, and it can be defined as a solution of the system star with the special initial conditions. It's not possible to give an explicit form for the fundamental matrix because of the nature of the delay systems. Based on the fundamental matrix, one can construct the Cauchy formula, that's the general form of the solution. It also can be considered as a semi-group that is constructed for the system. Based on such a Cauchy formula, in Kharitonov and Zhabkov work of 2003, the delay-Lyapunov matrix has been introduced. So this is a generalization of the Lyapunov matrix for delay-free systems. And it also can be compared. So I repeat that for delay-free systems, the state is a vector, is a constant. And the Lyapunov matrix is also a constant. But for time delay systems, the state is a function. And also the Lyapunov matrix is a function defined on the minus h segment. But the form is very similar, also an improper integral with the fundamental matrix under the integral. It can be shown that this Lyapunov matrix satisfies four properties. It's continuous, it satisfies this dual equation for the equation star, symmetry property, and the algebraic property. If the delay tends to 0 or matrix A1 tends to 0, then this algebraic property reduces to the classical Lyapunov equation for delay-free systems. Based on these four properties, a new definition for the Lyapunov matrix has been presented in Kharitonov and Zhabkov, and also you can look at the book of Kharitonov. By the way, it's translated, as far as I know, is translated in Chinese recently. The delay Lyapunov matrix is by definition is a function satisfying these four properties. And so this can be considered as a generalization of the Lyapunov matrix equation. It's also more general than the improper integral on the previous slide. Okay, so the next question is how to apply this for the solving of stability problems, robust stability problems for the system. First, we need to construct the functional V0. It's an analog of the quadratic form of Lyapunov function for delay-free systems. As you can see, this is much more complicated, but still is based on it's quadratic. and it's based on the Lyapunov matrix, here, here, and here. The derivative along the solutions of the system is a simple quadratic form. But there is a problem with such a functional. Let me come back. So the problem is the following. If you want to validate the exponential stability of the system, we need to check positive definiteness of the functional. But the problem is that except some very trivial cases, this functional is never positive definite. So we have there is no possibility to validate because it's never positive definite. This problem has been solved by Kharitonov and Zhabko. They introduced an additional term into the functional with W1, W2 to be positive definite matrix, such that this difference is also positive definite. And the derivative of this functional has this form. Now it has 3 summands. And this functional is called the complete type functional, and it has it's positive definite if the system is exponentially stable. So now there is no problem with the stability analysis. No, at least theoretically no problems. Practically there are some. Here is the basic criterion. The Tandeley system star is exponentially stable if and only if the functional v admits the quadratic lower bound with a positive number alpha 1. Also, it can be easily shown that the functional can be bounded by this expression from above, and its derivative also can be bounded by such expressions. From these inequalities, we can immediately deduce the exponential estimates for the solutions. First, we can obtain the inequality similar to exactly the same like for Delaunay-free systems, but with another number sigma. Then we can conclude that the function, this product is non-increasing, and similar to the Delaunay-free case, obtains the exponential boundary for the solutions. Next problem is the robust stability. And here also we can obtain some results with the new function, with the complete type functional. If we consider the nominal system and the perturbed system with a nonlinear, probably nonlinear perturbation, but which satisfies this inequality, so this linear inequality. Then we also can take our complete type functional V, differentiate it along the solutions of this perturbed system, and obtain 2 summands. The first summand is the same like for the nominal one, and the second depends on the perturbation. I don't want to give you the complete formulas for this linear functional L for some other numbers, but because they're quite heavy, you can look at the papers or its book. So here is the main result, actually. Zero solution of system delta of the perturbed system exponentially stable if nominal system is exponentially stable, and for 0 and for 2 efficiently. Again, these numbers mu1, mu0, mu2, you can find at the paper of Kharitonov and Zhabko, or better with more comprehensive analysis in the book of Kharitonov. Okay, and the last question is the following. The next question is the following. How to, so we can construct the exponential estimates with complete type functionals. We can analyze robust stability, but how to analyze exponential stability of the system? I show you again the functional, and it's easy to see that this is not a trivial task to check whether the functional is positive definite or not. I recall that that we need to check positive definiteness for the exponential stability of the system, and this actually this is a strong problem, but it has been solved with a number of results. Auxiliary results. again, I repeat the theorem of Kharitonov and Zhabko. Here, phi is any function of the space of piecewise continuous functions. There is no simple way to check such inequality for every piecewise continuous function. But in the paper of Medvedeva, now Alexandrova and Zhabko, another theorem has been obtained. The space of piecewise continuous functions has been replaced by the set S. Set S has this form, and its form means this set is compact in the Banach space of continuous functions defined, which are definite in -H0. So this is a compact set, and it's well known from the functional analysis that every compact set can be covered by an epsilon net. If we cover by finite epsilon net, so if we cover such set by finite epsilon net, then we don't need to check this inequality on every function of this infinite set. We can check it only on the points of the epsilon net. The number of points is finite. So we just need to check a finite number of inequalities. Of course, epsilon should be sufficiently small to don't jump from the positive definite estimate, positive estimate of the functional to a negative positive number here. But this sufficiently small epsilon can be found, and then we can construct explicitly construct the epsilon net. It can be constructed by different ways, but we found the best way. In our opinion, this is the best, because we don't need to compute. If we come back to the functional, if you substitute here an arbitrary function phi, we need to compute integrals. We need to compute many integrals. Of course, we don't want to. So our idea was to find such functions phi that we don't need to compute integrals, just need to compute some separate values of the Lyapunov matrix. And this has been found. Finally, we obtain this result. So I don't give any details because it's out of the scope of this presentation. You can find the details in these two papers or in some other papers of me and my colleagues from Mexico. So time delay system is exponentially stable if we don't leave this matrix Kr is positive definite. R is a natural number that can be computed based on the parameters of the system star. R reflects the dimension of the matrix Kr. What is the matrix Kr? This is a block matrix which is based exclusively on the Lyapunov delay matrix. So in some particular cases, you can see the form here. To compute matrix Kr, we need R different values of the Lyapunov matrix. As you can see, every diagonal consists of the same values. So such a criterion can be considered as a generalization of the classical Lyapunov theorem. And in fact, if H tends to 0, then this number R tends to 1, and this matrix reduces to the classical Lyapunov matrix. But of course, the problem for time delay systems is that it's of infinite dimensional nature. And that's why the dimension of this matrix Kr is not fixed. The dimension depends on the parameters of the system. So this is a problem, but probably it cannot be can be reduced because of the nature of time delay systems. So thank you very much for your attention. If you have any question, please.
Thank you very much. As far as I understand, the presentation, the overall direction is related to the stability, right? But maybe you could say a few words about optimal control for time delay systems. Are there any results or maybe numerical methods or something in this direction. Maybe it's not related to the presentation, but it's just it is interesting for me.
Yes, it's not related. Indeed. Of course, there are some results on optimal control. There are many papers on optimal control for time delay systems, but I should say that this is an extremely difficult problem, actually. It's much more difficult than for delay-free systems, but probably you know that this is also not trivial for delay-free systems.
So yes, yes.
There are some numerical approaches. Also, there is a numerical approach based on the Lyapunov matrix, but they are not simple. So you can look at you can find many papers on this topic, which is far from the closed state. So I mean, it's not closed even for linear time invariant systems. Not closed yet.
Okay, but it proves that this area is a challenging area, right, of control theory, the most interesting one, right? Maybe one of the most.
Yeah.
Okay.
Yeah.
Okay. Thank you very much. I think this month there are not too many presentations for the control theory from some universities from China, but your presentation, I think, was a very good push for this. So we will record all the sessions, and we will send all this information, try to attract to our seminar as more good professors in this direction as possible. So Alexey, thank you very much. We have several presentation participants.
Let me say some words. So indeed, we are open for the collaboration, and we already have some with professors from different countries, from Germany, Belgium, Mexico, and also China. But we are still open for some new collaborations.
Yeah.
Thank you for this, for the organization of this seminar.
Thank you very much. Thank you.
Okay.
Thank you very much. So the next presentation is the presentation of my PhD student Ildus Kuchkarov. But actually, I understood that maybe I would do this presentation better, so I will do the presentation myself. So let me start sharing the screen. 1 second. So 1 second. Yeah. So can you see the screen?
Yes, we can, Professor.
Okay. Thank you very much. So this work is related to the inverse optimal control theory and the approach that I'm working on, which is called the approach of continuous updating. And this approach comes from the theory of differential gains. In this paper, we particularly, with the colleagues from Karlsruhe Institute of Technology, apply this approach for the data from the driving simulator. So I will introduce to you what I mean exactly. So the small motivation. So motivation comes from the other presentation that is the screenshot of the first slide is presented here. So presentation of my colleagues for their work on assistance driving system. So what the system is, contains two agents or two participants, automation and a human. So when you're driving a car, you are a human and you interact with the automation or the car. And the car can be intelligent in the way that it can help you to, for example, reduce the fuel consumption and so on. So it is supposed that the automation has its own objective function, for example, reducing the fuel consumption, and a human driver as well has an objective function. What kind of objective function the human and driver has, it's a big question, and later on we will actually figure out what it is. So different type of objective function of a driver of a human means a different characteristic of the driver, different styles, different driving styles. So by defining the objective function, we can on this scheme you can see that by defining the objective function of the human, the automation can directly and automatically give a best response for his actions. So the automation needs to know the objective function. The human needs to know who is driving the car. So in the standard architecture of the system of my colleagues, they have offline phase and real-time phase. So that we are focusing on offline phase, where we need to study the objective function of the driver. And we had a paper that was presented on IFAC 2020 this year, and it was a kind of a first paper related to inverse optimal control with continuous updating. But this is it was quite it was more theoretical than practical. But this paper is related to the study of the data from the driving simulator that you can see on the right. So it works in a very simple way. So the human applies a steering torque, and the system calculates the state, which is a steering wheel angle and its angular velocity, using the system of differential equations presented below. So this happens actually at every current time instant t. And in this paper below, you can see the description of this driving simulator. So, but how this driving simulator was used? So, what you can see on the monitor, and what the driver see on the monitor is he sees the reference trajectory, or the reference value for the steering wheel angle. So, as when you are driving the car, you see the reference trajectory and you know where exactly you need to go. Yes, and what we observe through the simulator is we observe the control that the driver used and the real angle that he was. But most importantly, I want to point out now that as in the most of the real life situations, what we can see on the monitor and what the driver can see on the monitor is a restricted information, or constrained information, or truncated information. Means that when the driver is actually driving a car or driving a car in the simulator, the information horizon shifts in time continuously. When information shifts in time, the driver needs to adapt every time to the new value of the reference trajectory. So this means that if we want to model the behavior of the driver, classical approach for the optimal control does not work. Because what we need is not an optimal control of a driver that is defined some closed time interval. We need if we want to model his behavior, and then to use this behavior to solve the inverse problem, to define his objective function, we need to learn how to model this process. And this is called the continuous updating action. So what you can see on the slide now is actually the data that we study, yes, in this particular paper. And also in this particular paper, we do not only study the data, we construct a new model for inverse optimal control problem with continuous updating based on this data. So what you can see is the red line is the observed trajectory on the left, that was observed trajectory that was used by the driver, and the dashed line is the reference trajectory. So the driver saw a reference trajectory and tried to go along the dashed line. But the problem, of course, is that the driver is not perfect. His reaction speed is not perfect. His driving skills are not perfect. And what we want to model is this unperfectness. And there could be several things. And but our assumption is that their imperfectness can be modeled by the objective function that we try to find. So another interesting thing is that since our model takes into account a reference trajectory now, then it means that the system of motion equations and the payoff function of the driver that we want to model in order to solve the inverse problem needs to depend on this reference trajectory, or it should be non-autonomous. So we should have a non-autonomous term in our model, and this is another new thing in our result. This is a new our result. So what is continuous updating and why it is suitable? We think why it is suitable in our model. So a continuous updating approach can be defined for differential games, for optimal control theory as well. So it has two assumptions. The first one is that the system has information about motion equations and objective functions only on the closed time interval from t to t plus t dash. So at every current time instant t, we look ahead only for the t dash. Yes, and current time instant t evolves continuously in time. That what is actually happening when the driver driving a car, he has a information horizon that you saw on the screen, right? So so what we when we want to solve the inverse optimal control problem, what we need a concept of optimal control with continuous updating in order to solve inverse problem. So we use the simplest method, that's why we need it. And we say that an optimal control with continuous updating, we wanted to have in the form that for every current time instant t, this is the first point of the optimal control defined on the interval from t to t plus t dash. But when the current time instant t changes, the optimal control with continuous updating at time instant t plus epsilon is the first point of the optimal control defined in the interval from t plus epsilon plus t plus epsilon plus t dash. So these are very classical, not classical, but these are the assumptions from the continuous updating approach. So so this is the general optimization problem statement for the optimal control with continuous updating, but I will move on. We don't have so much time for this. So we will define of how to find an optimal control with continuous updating. And in particular, in our case, we consider a linear quadratic case. We consider, sorry, non-autonomous linear quadratic case where the integrand is a quadratic function, quadratic function, sorry, and the right-hand side of the motion equation is a linear function. So what is important now here? That first is that we have continuous updating, means that at every current time instant t, driver or a player orients himself on the integral from t to t plus t dash. So he tries to optimize his objective function on this interval, and this interval shifts in time. And the same for the motion equation. Another important thing is that we have a non-autonomous case, means that our matrices Q, R, A, and B in general case depend on the current time instant t. And this is exactly where we will put the reference trajectory. So this is why we need a non-autonomous case, to put a reference trajectory to construct an optimal control problem for the driver. So These are the necessary and sufficient conditions for optimality for the non-autonomous linear quadratic model with continuous updating. So this is actually very, I think it's very similar to the, this form of optimal control is very similar to the optimal control in the classical linear quadratic case. But the key difference is in the solution of the Riccati differential equation here. So first key point is that in here, the solution of Riccati differential here is not a kind of function of time here. We take only the first point of the solution of the Riccati differential equation over time, because our interval always shifts. So we solve some arbitrary optimal control problem on the interval from 0 to 1, and then we take only the first point of the solution and take it and put it into the optimal control, and then as the current t goes on, we update it. But there is a one problem. If we compare this optimal control with the autonomous case, when the right-hand side of the motion equation and objective function does not depend on the current time t, we will have a constant matrices here, and this mean that this would mean that actually it's very easy to solve system of Riccati differential equations. But in our case, this matrices depend on t, and actually the right-hand side of Riccati differential equation also depends on t. So now currently you are trying to figure out how to numerically solve this system and to obtain solution of Riccati differential equation as a function of t, because this system is can be easily solved for every fixed t, but we need an arbitrary approach. Yes, there should be something, so we are working on it now. But that's pure technical detail. Now, what we want to do, yes, by constructing an optimal control problem with continuous updating, we can, for every unknown parameter of the objective function of the driver, define his optimal control. And then by tuning the unknown parameters, we can easily find the curve of the optimal control that will be close to the observed optimal control, and therefore solving the inverse optimal control problem. So that's what we plan to do actually. So we have several unknown parameters, and also we suppose that t dash is also unknown, meaning that the information horizon of the human of the driver is unknown. This I will comment on this little later. So we use the simplest form of the inverse optimal control problem, where we need to find the unknown parameter of the objective function of the driver, or in the inverse optimal control, in order to minimize this this functional. You can see that this function, the meaning of this functional is the squared. It's a distance between the observed trajectory and control and that we see on the driving simulator, and the optimal trajectory and control as a function of the unknown parameter. So we just define the unknown parameter so that our optimal control and optimal strategy fits the data. And so the most interesting part, this is the model of the driving simulator, yes. And so the state vectors we have already discussed, the control is also already discussed, and this is the system dynamics. But we need to change the system dynamics of the simulator into the system dynamics of the driver. So as you remember, the system dynamics of the driver only consisted of matrices A and matrix B. But now we need to include into the model of the driver the knowledge about the reference trajectory. So knowledge about the reference trajectory comes into the system of motion equations as a function ht, where we use some tricky constructions in order to include the reference trajectory into the motion equations. And then we include this information to the objective function. And as a result, by using this matrix T, we say that the driver, the objective function of the driver is to go as closer as possible to the reference trajectory. So this we have modeled the driver in this way. Yes, it's a simple model, but anyway. And what we want to define, the unknown parameter here, are the matrices Q, R, and parameter T dash, so his information horizon. So matrix Q and matrix R are the parameters of the objective function that define of the character of the driver, about the speed of his reaction, maybe even about his will of going along the reference trajectory. Maybe if the value of his value of parameters Q are very small, means that he actually does not care about the reference trajectory at all. He just moving, straight through the country, straight through the field, and does not care about the road. Yes, and the T dash is the value of the information horizon, meaning that how far can he predict his actions, how far he thinks ahead. That's also very important. And again, this is the data that we studied. So what we did is we solved the inverse optimal. So we managed to solve this inverse optimal control with continuous updating and reference trajectory. So it's kind of non-autonomous inverse optimal control. And what you can see here on the slide is the difference between the solutions of this problem for different fixed parameters of T dash. You can see we try to change T dash, and also we consider the results with the case when we don't have continuous updating. But this is important. So the data that we have studied is the data when a human first time used the simulator, meaning that he did not know any information about the reference trajectory, and he actually was acting as the information was continuously updated for him. So so you can see for different T dash and for non-continuous updating, you can see that the value of the objective function for the inverse optimal control is actually getting smaller when we go to the value of T dash close to 1. This means that, well, this actually means that the driver did not know the whole reference trajectory, meaning that there was continuous updating in some sense. Yes. And actually, this means that the driver was not very, I cannot express this in English, I'm sorry, far-looking guy. So I know the real value of the information horizon that was available to the driver in the simulator, and it was 2 seconds. So when you remember that monitor, yes, I will show you. When you receive this monitor, the time from the point up to here is 2 seconds. So he had information about 2 seconds in front of him. And what we haven't obtained is that his optimal T dash, or his real T dash, or according to our model, is a little bit more than 1, but less than 1.25. But I will show you this later. Yeah, and these are the values of the Q matrix. Yeah. So let me show you some simulation results also. So based on this data, we have simulated an optimal control. the difference between different values of optimal control with different T dash and without continuous updating. So first, let's have a look at the U real, which is a dashed line which shows the control that was actually used by the driver. So that's what you can see, yes. And now optimal control without continuous updating, you can see it's totally wrong. So it's impossible to apply the classical optimal control theory, classical optimal control approach to model this kind of online updating environments. But the case with continuous updating for different values of T dash shows a very different results. You can see in this corners, we can see that we are almost able to copy the behavior of the driver. But anyway, there are ways for the improvement, and we are working on it. You can see it not perfectly matches, yes, the solution, but we are working on it. Yeah, since it is a real data from the simulator, there are also other kind of small problems. But you can read our paper from IFAC 2020, and there was a theoretical synthetic data, and there we match almost 100% the data. So here you can see the real trajectory now. That was control, now trajectory, and this is the this is a optimal trajectory without continuous updating. Again, you can see that it's totally different from what the driver is doing actually. And what you can see is that the case of T dash equals to 1 is closer from other optimal control with continuous updating to the observed one, which is interesting. This is another state variable. So again, we can talk about it again, but maybe no. So now the last case, but the last but not the least. So this is the solution for the optimal T dash. So before I was showing you the results when we fixed different values of T dash and then found optimal Q values and R values. But now what we do is we also find optimal T dash using an inverse problem, meaning that we understand how far away the driver looks when he is actually driving the simulator. And this is the value. And it means that his information horizon is a little bit more than 1 second, which is actually pretty close to the reality that we have in the real life. When the driver is driving a car, he predicts his actions maybe for 1 or several seconds ahead. So that's interesting. Yeah. Also, we need to take into account that the monitor has had 2 seconds interval, 2 seconds horizon. So yeah, and this value, if we can compare this value of the inverse optimal control problem functional, it is less than the others with fixed T dash. So that also proves that the approach for optimal T dash is suitable. So a few words about the conclusion, but maybe I'm running out of time. So this work is a prolongation of the paper from IFAC 2020, when by the introducing of by studying the real data, and then as a result we had to introduce a reference trajectory in the model, and then we had to change model from autonomous to non-autonomous case, which is that's a plus. We understood that T dash lies into the acceptable interval from 1 to 2, which is true. Future work, we need to reduce the computational complexity, because now in order to solve this inverse optimal control problem, we spend a lot of time because of the non-autonomous case, that the problem I mentioned for the Riccati differential equations. Next thing that we want to do is we want to, after we solve the complexity problem, we want to compare we also have different data from different drivers, different of the simulator, and then we want to compare them, and then to have a to give a conclusion. We want to show that actually by this approach we could try to define who is the driver, try to define his skills using this matrices Q and R and T dash. So, and then another thing that we are working on is related to the Bayesian approach. So I think next month there will be a presentation about the Bayesian approach for dynamic games, not continuous updating, but Bayesian updating. And we plan to introduce a model where the driver will be able to update his future information about the unknown reference trajectory. So when you drive a car in the simulator, not one time, but several times, you start to learn the reference trajectory, start to learn where to go on the right, where to go on the left, and then this means the training, this means the Bayesian updating about the information about the reference trajectory. So, and that's interesting to define the optimal, to define the learning rate of different humans and to compare. This is another kind of parameter of the human, his learning rate, right? So this is a list of papers related to the driving simulator and so on. These are our papers for the continuous updating approach for linear quadratic case. Some paper about the bilevel method, how it is used. Some paper about Hamilton-Jacobi-Bellman equations. And this is the list of other papers related to continuous updating approach. These are different things for differential games, like linear quadratic case, open loop, closed loop, HEB equations, Pantragen-Markström principle, cooperative differential games with continuous updating, Pantragen-Markström principle, non-Pantragen. This is for IFAC 2020, and a lot of other things related to continuous updating, and also several different papers which I find to be related to what we are doing. So these are connected to the stability control. Actually, what the authors are doing here in the several papers, they construct an optimal control problem in the way that we do it on the interval from t to t plus t dash, and then also linear quadratic. But the key point there is that using this model, they built a stabilizing control. So I would say that the technique is very close, yes, but how they do it and for what they are doing, it's totally different. But anyway, I wanted to mention that because I think it's very good that so I'm not the first one to do this, and I was very happy. So that it means that it's possible. Okay, thank you very much. So so the next presentation is the presentation of Anna Golovkina, model-based optimal control of transmutation strategy in accelerator-driven system.
Okay, I hope it's visible. Okay, so my today talk is dedicated to model-based optimal control of transmutation system in accelerator-driven system. And first of all, I would like to say several words about the motivation of this research. I think all of you know that the most critical problem of nuclear energy is the production of radioactive waste. An average power plant creates about 20 metric tons of waste per year. And for example, in Russia, there are 37 such nuclear plants. That means 740 metric tons of waste is produced every year. That's quite a large quantity. And how this problem is solved nowadays? Nowadays, spent fuel is classified and placed in geological waste repository deep underground. But as you can see from this picture, The main problem of this storing approach is that nuclear waste contains a lot of long-lived isotopes. These isotopes include fission products and transuranic elements. And as you can see from this slide, the long-term radiotoxicity is dominated mostly by plutonium and other actinides, corresponding to the blue and red line on this picture. This level becomes equal to the radiotoxicity of uranium ore only more than after 100,000 years after the fuel was discharged. This means that the safety of this geological repository should be provided for more than 500 years. And this is quite a long period of time. And I think that we can be 100% sure that the storage will be safe during all this time. But what we can do? Preliminary treatment of nuclear waste potentially can reduce the disposal time by 4 orders of magnitude. As we saw with plutonium and other transuranic elements, they give the main contribution to the long-term radiotoxicity of waste. So first of all, these isotopes should be separated from the others. And after then, we can try to convert them into short-lived or stable by neutral or charged particle fluxes. This process is called transmutation, and I will focus on this further in my presentation. The facility to perform this transmutation we will consider as accelerator-driven system, which is now one of the promising types of advanced recycling reactors. Its main parts are the proton accelerator, spallation target, and subcritical core. Due to the core subcritically, this let us introduce some atypical actinide mixtures inside it, because the external neutron supply necessary to maintain the nuclear chain reaction inside the core comes from charged particle beam interaction with the target. Our goal with respect to this physical problem is to minimize the radioactivity of spent fuel by the time moment T, capital T, which we denote the end of the company. And we try to solve this problem using optimization technique. So we want to define the amount and the composition of charged fuel in the initial moment of time in order to achieve the minimal radiotoxicity by the end of the campaign. Okay, now I should switch to the mathematical formulation of this process. And at first we should begin from the mathematical modeling part. So we should build the mathematical model that would further be underlying our optimization framework. So dynamics of fuel isotopes concentration is described by Bateman equations 1 with the initial condition 2. Here I is the index of our isotopes considered in the system, and small n is their total number. Coefficients in these equations, they are found from transmutation chains. So the transitions between our isotopes we considered in our systems. They are constant, and they are evaluated by some EIA organizations, and they are publicly available. Okay, but it's more convenient to operate with these equations when we use the matrix representation of them. So we split the system 1 in 2 parts. We separate it in linear and non-linear parts. The linear part is described by the matrix A lambda, and the non-linear part is described by the matrix A phi. The non-linearity in this matrix comes from the indirect dependence of coefficients in this matrix on the state of the system 3. And from where this dependence coming from? we will discuss now. So nonlinearity of this reaction path has a very complicated structure. It's caused by the strong dependence of the neutron spectrum on the densities of nuclear composition fuel, and then comes from the solution of the equation number 4. That should be solved with the proper boundary conditions. Here we denoted it by 5. Okay. If we solve the equation 4, we will be able to compute the nonlinear coefficients in our matrix AFE by formula 6. Okay, but in order to obtain these values, we need to solve two-dimensional differential equation, and also to integrate it double time through the energy and through the volume. So it's quite complex, and to get rid of this, we switched to multi-group approximation of our equation 4. It's widely used to discretize the continuous energy variable corresponding to the energy in the range from minimum to maximum energy. If you write down the equation 4 for the Hopf energy group in one-dimensional cylindrical geometry, equation 4 will take the following form, and the boundary condition will be also shifted to the form 8. Now it's simpler to calculate the expressions for the coefficients because to solve these equations, we can use some standard numerical techniques based on finite difference or finite element discretization. And using this, we can also substitute our integration with respect to the energy and with respect to the volume, like Riemann sums, and get the formulas to calculate the coefficients in matrix AFE in the form of 10. Okay, but also during our calculations, we should take into account the constraints on effective multiplication factor. As I said in the beginning of my talk, we want to use a subcritical reactor in order to transmute our transuranic isotopes. Subcritical means that effective multiplication factor in it should be less than 1. So that we need to introduce the additional constraint to our optimization problem that can be expressed by the non-equality 11. But how can we compute this efficient multiplication factor? The mathematical sense of this value is the largest eigenvalue in the eigenproblem corresponding to equation 12. But of course, this means that we should additionally solve this equation at each iteration in order to be sure that we didn't exceed the constraint 11. It involves some additional computational efforts, and we want to get rid of it. So we decided to use physical interpretation of efficient multiplication factor given by the formula 13. Its physical interpretation corresponds to the relation of number of neutrons appeared in our system to the number of neutrons which is disappeared during the leakage from the volume or to absorption with some isotopes inside the core. Using formula 13 and write down the underlying expressions for each quantity in this formula, we will obtain the representation of our efficient multiplication factor based on n, which we computed previously here. The same quantity we can use for this formula. And if we combine the comparison of efficient multiplication factor computed as an eigenproblem of 12 and approximation 13, we will get a good quite good coincidence. Moreover, approximations gives us an upper boundary of this equation. So if we use it in the inequality, it guarantees us that we won't exceed the value 1. Okay, resuming the mathematical modeling part, we can shift to the optimization framework and to describe how we solve it. Optimization model for this problem can be formulated as problem 14, where we want to minimize function f with respect to the given system of differential equations and inequality GL. Okay, f is our cost function characterizing the reductivity of unloaded fuel after time period Tn. In order to get rid of this inequality of our constraint, we want to generalize our cost function and introduce some penalty in the form of logarithmic barrier and just to optimize this generalized function 15 in order to solve our optimization problem. Okay. We tried to use gradient-based optimization methods. Thus, we need the explicit expression for our gradient of the cost function. If we write down it in the form 16, we will see that in order to compute it, we have to calculate 3 derivatives that is here. And further, we will discuss a little bit how I did it. So the first one, okay, I thought that I might be a little bit longer than I try to speed up. Okay, so based on the conditions of the theorem of ODE solutions differentiability with respect to initial conditions, we can find the first derivative in our equations, and if we substitute all the variables, we can come to this formula. Then in order to compute this derivative is quite easy, it's very simple. In the end, we want to use quasi-Newton optimization algorithm because we have a nonlinear programming problem, and quasi-Newton's methods are widely used in order to solve such problems. They don't require to compute the second derivative, so we just use some approximation that is updated on each iteration by using gradient evaluations. Optimization algorithm is presented here. As an extra neutron source, we used such dependence in order to solve our equations. And in the end of optimization, we came up with these results. So in order to sum up, I would say that after this optimization was performed, it was able to decrease the radiotoxicity of our fuel in 5 times. So a brief summary of my talk is here. I think I won't read it. The most valuable result I already sounded. So by implementing this optimization technique, it was possible to reduce the radioactivity in 5 times. Yeah, thank you for your attention.
Dear friends, now presentation is the last one, but we put it this time, and is a master student from Yan University, and her professor is Li Jiangrong.
Yes.
Her title of report is State Feedback Based Fuzzy Control Design for Discrete Time Interval Type 2 Fuzzy Linear Delay Systems. Please share your screen and show your presentation. Thank you.
Okay. Hello everyone, welcome to my report. My name is Li Lian, and I come from Yan University. The topic of my presentation is state feedback-based fuzzy control designed for discrete time interval type 2 fuzzy bilinear delay systems. It contains its purpose. Introduction, problem formulation, main results, numerical example, and the following work. And now let's see the first part, introduction. The application of the bilinear system. Bilinear systems are widely applied in various fields. Bilinear models can describe many physical systems and dynamical processes in engineering fields. Bilinear systems can achieve better control of nonlinear systems. The problem of stable analysis and controller design of several bilinear systems have been studied, including discrete time and continuous time cases. Next, the application of interval type 2 fuzzy systems. Interval type 2 fuzzy systems can provide a better performance for the nonlinear systems. Interval type 2 fuzzy system uses lower membership function and upper membership function to deal with the uncertainty of the problem. Many research results have been obtained for interval type 2 fuzzy systems. The motivation of this paper. The problem of discrete interval type 2 fuzzy bilinear systems with constant delay has not been considered and remains to be challenging, considering the uncertainty in the membership functions. The nonlinear systems are modeled into the interval type 2 fuzzy bilinear systems. Based on the Lyapunov stability theory, an interval type 2 fuzzy state feedback control criterion is proposed to guarantee the interval type 2 fuzzy closed-loop bilinear system to be stable. The fuzzy controller can be obtained by using sequential linear programming matrices method. Now is the program formulation. Consider the following discrete interval type 2 bilinear system described by the following equation. You can see the equation 1. And in this equation, the xt denotes the vector of the states, ut denotes the vector of the control inputs, and yt denotes the vector of the control outputs. And in this we can see the d is constant delay. By using some methods, and the fuzzy model 1 can be expressed by the following global model. We can see the equation 2. And this is the upper grade of the membership, and this is the lower grade of the membership. Then we consider the interval type 2 fuzzy controller with L rules is of the following form. You can see the equation 4 and the equation 5. And we choose the special form sin theta and cosine theta in order to make the nonlinear systems become linear systems. Then the state feedback controller of the whole system can be expressed as the following equations. Then with substituting the equations 8 and 9 into 2, the closed loop systems can be rewritten as the following equation. You can see the equation 11. And for convenience, the following marks are made. Next is the third part, main results. First, theorem 1. The closed-loop system 11 is astatically stable if the following matrices inequalities are held. You can see the inequalities. This. Let's look at the proof process of the theorem. We choose the following Lyapunov function. Taking the forward difference of Lyapunov function 17 with respect to 11. We can see the equation and we can get the equation 18. From the theorem 1, and we can know that the difference of Lyapunov function is less than 0. From the theory of Lyapunov stability, it can be known that the discrete term interval top to fuzzy Berliner closed loop system 11 is aesthetically stable. The next is theorem 2. The discrete term interval top to fuzzy Berliner closed loop system 11 is aesthetically stable if the following matrices inequalities hold. And in this theorem too, we get a new equation, the equation 22. The next part is numerical example. In this section, we provide a numerical example to show the effectiveness of the results obtained in the previous section. The system matrices, primotors, and scalars are given in the following. You can see these matrices and some scalars and primotors. Then we choose the following lower and upper membership functions for the discrete term interval top to fuzzy Berliner system. You can see this equation. The membership functions of the controller are given as follows. In the simulation, the state response of the closed loop system is shown in the first picture, and we can see the first picture simulation of state. And the control input ut is shown in the second picture. This picture is a simulation of input. And it can be seen from the simulation results that the closed loop system is aesthetically stable under the designed controller. And the final part is the following work. The fuzzy Berliner state feedback control problem of discrete term interval top to fuzzy Berliner systems with time varying delays and infinitely distributed delays are also worthy to further study. And that's all. Thank you. Thanks for your attention.
Thank you very much. A very interesting presentation about the stabilizing control. Do anyone have any questions?
I have one short question.
Oh, okay.
You consider discrete type systems. Is it possible to deal with continuous time?
李莲老师可以帮我翻译一下吗？不好意思。
您稍等一下，我刚才在回复信息。
好。
Ви не можете повторить вопрос? Она не понимает, можно по-русски.
Вот она рассматривает дискретные системы,
Да.
а непрерывные системы можно рассматривать, можно изучать таким же методом?
Непрерывный.
Да, continuous time, да.
OK，就是你讲的是离散的是吧？
对，离散的。
他想问这个连续的可不可以啊？
因为我现在
用英语来回答吧。
用英语吗？
你英语来再试试回答，锻炼一下吧。
It's okay. But I don't have some work in the continuous systems.
Okay.
可以听懂吗？
Okay. Thank you.
Okay, thank you.
Okay, thank you very much. That was a very interesting presentation. Actually, this is it. So we have finished the seminar. I wanted to thank everyone for participating, for listening, for doing presentation. Especially, I wanted to thank our participants from China, because I know that in China it's already more than 12 p.m.
Not.
I'm very
Right.
sorry for this. We had to start at 11 a.m. Moscow time to prepare ourselves. So I think next time we will start much earlier so that we could have balance. And thank you very much. I hope that some of the participants could already find some connection points. I myself have found 2 ways to cooperate, and therefore thank you, Dr. Lin, for organizing this. That was a great work. Thank you very much. Yeah, especially thank you for all of the guys who presented their efforts. Инь, хочешь что-то сказать?
По-русски первый. Сначала очень благодарю всех, приходили на семинар, и очень вы делали очень прикольную презентацию. Это первый раз мы организовали этот семинар. Не так хорошо, но мы надеемся, что в будущем наш семинар будет чем дальше тем лучше, и наша кооперация чем дальше тем лучше тоже. И сегодня целый день, почти 8 часов на выходные мы здесь работали, и благодарю вас за участие на семинаре. 非常感谢大家参加我们的这个讨论会，它并不是一个正式的会议，只是我们过去学习的一个方式的一个拓展。我们想着有更多的团队和各个方向的朋友同行、老师、学生，然后能一起交流。第一次组织没有什么经验，所以今天既超时了，也中途发生了很多没有想象到的一些小插曲、小问题。我们希望在将来的时候能把这些问题都在讨论会里面能避免掉，然后让我们的讨论会越来越好，使得我们将来既可以在讨论中学习到东西，也能得到我们想要的合作和科研成果。然后非常抱歉拖了这么晚，就是对国内的同学老师来说，这已经非常晚了，辛苦大家了。
Okay, so I received some thank you by chat. So thank you everyone. I stopped recording, so we stopped the official part. 1 second.
Можна пригласить Ілля